G'day guys, Socket here. Today's tutorial is called The Language of Sound, and I'm making this because up to now we've been taking measures and creating house curves and doing EQ work and stuff, and we haven't really had to worry too much about the technical aspects of sound and things like that. But we're moving on to the next stage of the tuning process, which is time alignment and phase alignment. And this stage is a little more technical than the previous stages. And so it's important that we understand things like phase shift and cycles and things like that, so that it'll make our timing and phase alignment activities make a lot more sense. But before we go on, I just need to give some credit to a bunch of people that I borrowed some of the animations for the making of this tutorial from. And so that would be Jacob at Animagraffs, fabulous website where he does a whole bunch of 3D animations. Yeah, just great. And then Kyle at Audio University. He's got some great videos on audio engineering and the basics of sound and stuff like that. Really worth checking out if you want to know more about that. And then finally, Dr. Dan Russell at Penn State University, so the Penn State website, where he's got a bunch of acoustic and vibration animations that he uses in teaching his physics students. Once again, a great resource if you want to get super geeky and understand all the techie stuff about waves and wave formations. It's a fabulous site to go and visit. I'll put all the links of these sites down in the comments. With that out of the way, let's go and talk about the language of sound. So what is sound? Well, sound is waves of high and low air pressure that travel through the environment and eventually reach your ears. And then your ears hear that alternating high and low air pressure and convert that into an electrical signal that your brain interprets as sound. Now, a speaker creates sound because it has a motor and a cone that move back and forth. And as the speaker pushes in and out, it creates an acoustic pressure wave that travels through the air. So when the amplifier applies a positive voltage, the speaker pushes out, and when the amplifier applies a negative voltage, the speaker cone pulls in. And that's why speakers have a positive and a negative terminal on them, so that you can wire up your amp to your speakers correctly. And if they're flipped, for example, you have the positive from the amp connected to the negative terminal on your speaker, the speaker will pull in when it's supposed to push out, and vice versa. But let's talk about that more later. So if we take a look at a slow motion video of a speaker, we can see this push-pull cycle in action. We can see how the voice coil or the motor is pushing and pulling the speaker cone. And each time it does, it goes up and down, it creates a pressure wave that kind of looks a bit like this. So as the speaker cone moves back and forth and back and forth and back and forth, it creates alternating waves of positive and negative pressure that ripple out like waves on a pond. But waves on a pond and waves in the air are two very different things. So let's talk about how sound travels through the air. So air is not just empty space, it's not a void. It is actually made up of molecules of gas, 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, and about 1% everything else, including water vapor. So these gas molecules are pushed and pulled by the speaker cone to form pressure waves. So as the cone pushes out, the air molecules are bunched together to form a high pressure wave, because there are now more air molecules being forced into the same area than before, and then they bump into other air molecules and cause a ripple or a disturbance in the air. And as the cone pulls back, it creates a low pressure wave as the air molecules rush towards the cone to fill the void. And it's this alternating high pressure, low pressure wave that we describe as sound waves. This wave or disturbance through the air moves at a constant speed that we call the speed of sound. Now, if you're in the metric system, that's 343 meters per second or 1235 kilometers per hour, right? Or if you're in the empirical system, that's 1125 feet per second or 767 miles per hour, which is bloody quick and explains why sound fills a room, or in our case the cabin of our car, instantaneously. But it's not that the air molecules are moving at those speeds, it's the pressure wave or the disturbance that moves through the air that is moving at that speed of sound. But of course we like to listen to sound or music inside a small glass-lined box which causes the waves to bounce off surfaces and collide. For example, when the pressure wave hits a surface, depending on what it is, it will either be reflected or partially absorbed. And then when two or more waves crash into each other, they can either sum up and get stronger, or the waves can cancel each other out, or anything in between, to be honest. So, for example, you can see here in this little illustration how the waves are summing up in some parts and the waves are cancelling out in others. And it's these cancellation lines that show up in our measures as sharp dips. And then our speaker cones flex and distort, a bit like it's particularly evident in subwoofers, which causes the pressure wave to create strange interference patterns, like in this illustration. So it's no wonder with all of this going on, it's difficult to get a tune, a car audio tuned properly and dialed in to sound crystal clear. Well, with a microphone and software like REW, it is entirely possible to get a great tune. That's if you understand what the measurements and the information being displayed in REW means. So let's talk about how to take what we've just learnt about the physics of sound and how to translate it into the world of Room EQ Wizard. So first of all, we need to understand that REW is basically a massive complicated calculator, and like most things in audio engineering, it runs on maths. But don't worry, we're not going to get into a bunch of formulas and stuff. We just need to be aware that we can't see the sound waves and the phase lines and stuff in REW. To see these things in real time, we would need to use a tool like Smart V8, but that's for another tutorial series. How sound engineers and REW convert speaker movements and pressure waves and things is by using sine waves. Now, you have probably seen them before, but let me walk you through an example. Okay, well, this is a sine wave, and it's a mathematical representation of the pushing and pulling motion of the speaker. So it sort of starts down here at 0 degrees, and then as the speaker pushes and gets to its maximum excursion, it's reached what we call 90 degrees in the cycle, and then it starts to return back to its default position, and then it's back to its default position, and then the amp sends a negative voltage signal to the speaker, which pulls the speaker cone back, creating this dip until it's to the point of maximum inflection, and then it returns back to its center position again, and it's completed one in and out cycle, and then the process repeats over and over and over. So these percentages, 0, 90, 180, 270 and 360, describe the different stages of that speaker oscillation cycle. And so when you look at it and think about the speaker moving in and out, this is positive voltage, right? And it's pushing the speaker out, and the speaker is pushing those air molecules away from it and causing a high pressure wave. And then below the line is a negative voltage where the speaker cone is being pulled back, and this is causing a low pressure wave where the air molecules are rushing in to fill the void created by the membrane of the speaker cone pulling backwards. And so we have this high pressure, low pressure, high pressure, low pressure cycle going on, and this is represented mathematically as a sine wave. So let me use another illustration to try to connect air particles and this new concept of sine waves. And so in this illustration you can see there's this sine wave shape moving through the particles of air. It's made up of that high pressure ridge or positive ridge and that low pressure part of the sine wave following behind it. And as the sine wave or the pressure ridge moves through the air, you can see it pushing all of those air particles or bunching them up in front of the pressure wave, a bit like a surfer surfing on the crest of the wave in towards the shore. And it's that disruption in the air, that high pressure ridge in the air, that we hear as vibrations in our ear and interpret it as sound. Okay, so now that we understand that the sine wave is a mathematical representation of the speaker movement, let's take a closer look. Now, I'm going to use a tool called Desmos Sine Graph, I think it's called, to explain a little bit more about the sine wave. And I'll put the link in below, but let's go open up the tool. So here we have a sine wave. It's sort of representing, the up-down movement of a speaker, and this orange part here represents, one cycle within this sine wave series. And so we're starting at 0, and here's 90 on the sort of the outwards push of the cone, and then here's 270 with the cone is all the way sort of inflected, for want of a better term, and then this is the end. So this is one cycle, right? And you can see that sort of cycle, repeats over and over and over. And if I zoom out a bit, you can see it. You can see it repeating there, and then again, and then again, and then again. And so these are each one of these from beginning to end is called a cycle. And so if you are completing one cycle per second, that's called 1 hertz. So if you've got a subwoofer playing a 40 hertz tone, that means that the subwoofer is literally vibrating or going through this in and out oscillation 40 times a second. And if you think about it, if you've got a tweeter playing an 8,000 kilohertz tone, that means the tweeter is moving back and forth 8,000 times a second. And to me, that is just nuts. But it explains why subwoofers are large and tweeters are very small. I mean, you can imagine trying to get all of that mass of a subwoofer to move back and forth 8,000 times a second. So one of the things I've always found fascinating is just how sensitive the human ear actually is. I mean, we can hear something that is vibrating at 20 times a second all the way up to something that's vibrating 20,000 times a second. It's absolutely incredible. Now, that said, it really does depend on how old your ears are, because if your ears are, for example, 45 years old, they're probably taken a bit of wear and tear over all those years, and you're probably not going to hear to those extreme levels. But just to show you exactly just how wide that range of frequencies is, I've got a little sweep tone that I'm going to play now. So just check to see how your hearing is, and see how low you can hear and how high you can hear by listening to this track. So how did you go? I'm pretty sure everybody would have been able to hear the 20 hertz tone, and some of you might have even been able to hear 18, 19, maybe even 20,000 hertz. I know that I struggle at about 14 to 15. It's, to me, I can't tell beyond about 15 whether there's something there or not. But that's quite normal. As you age, your high frequency sensitivity becomes diminished, and you're not able to sort of hear those super high frequencies anymore. But I didn't put this exercise in to give you a hearing test. I included it so that to demonstrate the relationship between cycles per second and the pitch of the sound and how we perceive that with human hearing. So if you want to play around with that, I'll put a link to the tone generator or that sweep generator into the description of the tutorial. Go and have a play around. What I found surprising when I first started mucking around with this was most of the frequencies that we would associate with the bulk of the music that we listen to generally occur below 2000 hertz. Everything above that is, when you actually listen to it, is ear-splittingly high, in my opinion. But certainly go back, play around with that tool. Get used to listening to things like a 100 hertz tone or a 250 hertz tone or a 500 or 1000. Getting to know those sounds will certainly help you when you're doing fine tuning of your car audio tuning. So now that we know what a frequency is and we know what our upper and lower limits are to human hearing, and we've got a vague idea about how pitch changes as frequency goes up, let's go back and look at the other characteristics of the sine wave. Okay, so let's go back to our standard sine wave. Now there are three things that we can change about the sine wave that I want to sort of take you through. So one aspect that can be changed that we kind of already talked about is the frequency, right? So, oops, that's not the frequency. This is the frequency here. So the more cycles that we go through in a second, the higher the frequency, right? And the higher the frequency, the higher the tone that we detect, when we're listening. So, if I turn it up like this, we can see here is the original measure, but now we're going through, let's say this was 100 hertz before, right? Here's the original measure. Now we're going through 1, 2, 3, 4, 5. So this new measurement would be 5 times 100 hertz, which is 500 hertz, right? So we can change the frequency by in our sine wave series by changing the number of cycles that we go through every second, right? So I'll just put that back to its original setting. So the second aspect of the sine wave that we can change is the loudness or the volume, and this is called the amplitude. So we can add extra voltage and cause the sound level to go up. So we're actually adding energy to the speakers. That means that it will push more air on the high pressure. When it's pushing out, it's going to physically push more because it's got more energy and it will sound louder. Okay, and we can ultimately reduce the amount of energy going to the speaker. It will push less, and it will sound quieter. And this is exactly what your volume knob is doing in your car. When you're turning the volume knob, it's a bit like using a tap. You turn on the extra flow of electricity or reduce the flow of electricity to the speakers. Okay, so that's the second thing that we can change with our sine wave, the amplitude. So the third way that a sine wave can be changed is by adding time or delay, which results in what we call a phase shift. The amount of shift is measured in the degrees, or so for example 90 degrees out of phase would represent 1/4 of a cycle. Okay, and so we sort of measure that from the starting point, or the time zero, to how many degrees or fractions of a cycle that the sine wave is shifted. So this would be, for example, 90 degrees, and this would, for example, be 180 degrees. Okay, so there are three different ways that the sine wave can be changed. As we said, phase shift, we can change the frequency, or the sine wave could have a different amplitude. So we've been largely looking at single speakers, and let's go and have a look at what happens when multiple speakers are played together. So if there's one thing I want you to take away from the tutorial so far, it's that a speaker operates by pushing and pulling the air, and it goes through this cycle hundreds, thousands of times per second. Now, if we just had one speaker playing in our car, then we wouldn't really have to worry about a whole bunch of things. The only thing we really have to worry about would be reflections. But we use more than one speaker in the car, and if we have two speakers playing together, think of them like two guys in a rowboat, right? We want them rowing together or working together, not fighting against each other. So when we have both speakers pushing out at the same time and both speakers pulling in at the same time, then we get maximum summation and maximum deflection, as sort of shown in this first diagram, and we would call those speakers in time and in phase. Now, the opposite is true when we have one speaker pulling and one speaker pushing. Then they're working against each other completely, sort of having an arm wrestle, and we get absolute cancellation. So, the positive pressure is being basically cancelled by the negative pressure wave being caused by the other speaker. And then we have somewhere in between where they're not quite in sync, and one's pushing at one time, or they're pushing together, but they're not, as terms of sine waves, completely in line. And so you'll get somewhere in the middle where you'll get some loss of volume. And people often complain that their subwoofer's not sounding bassy enough, and usually it's because of a timing issue or a phase issue where the subwoofer is not playing in time with the other speakers, and you're losing some of that subwoofer energy because of it's pushing when the other speakers are pulling, and causing cancellations, right? So there's a number of things that can help or hinder us in terms of trying to achieve all of our speakers in time and in sync. One of those things is polarity. Have we got our speakers and things wired up properly? Let's go have a look at that, and how having your speakers incorrectly wired can actually cause you a bunch of headaches before you even get to time and phase alignment. So let's talk about polarity, and we touched on this earlier in the tutorial, where we talked about the amplifier and the speakers having positive and negative terminals. And so when you wire positive to positive and negative to negative, then the speaker is in the correct polarity. And if you wire positive to negative and negative to positive, then the speaker will be in the incorrect polarity. And so when you have two speakers that are wired in with the correct polarity, they will both be pushing and pulling at the same time, and the resulting sound that they will make will sum up. It will be louder and crisp. If the if you have one speaker with the correct polarity and the other one wired incorrectly, then when when they are playing, one will be pushing and the other one will be pulling, and you will get them fighting against each other, and you will end up with cancellation. That kind of makes a bit of sense. The question is, it's often difficult to find out whether you have a polarity problem. It usually happens when you're doing the install and the wiring gets mixed up, or you plug the wrong RCAs into the DSP in the wrong order, or something like that. It's usually a wiring problem. Polarity is a wiring problem, not a delay problem. So it can be fixed in the DSP by flipping the polarity. That's the way that you can correct it, but ideally you can flip the wiring somehow by rewiring the speakers or changing the RCAs in your DSP and get rid of the polarity problem itself. So how do you know if you have a polarity problem? There are three basic methods. One is to play both speakers with correlated pink noise, put your head in between the speakers and see whether you can hear the speaker in the center, or the sound in the center, or the sound being pulled to one side. If it's being pulled to one side, then it's pretty likely to be one of your speakers is out of polarity. Now that can be quite difficult to hear with the high frequencies like your tweeters. So another way of checking polarity is to look at the impulse response. If you've been taking sweeps and you have that impulse response information, the peak of the impulse will be pointing up or down, and if you look at your two speakers, such as two tweeters or two mids, you should be able to see the peak of the impulse response both pointing up or both pointing down. But if one is up and one is down, then it's likely that one is a polarity incorrectly wired and you have a flipped polarity somewhere. And the third way to do it is to measure for example, your left and right speaker with uncorrelated pink noise or a sweep, and then play both speakers together with correlated pink noise or a sweep, and see whether the two speakers together are playing louder than each of the individual speakers. If they are, and they're playing 3 to 6 dB louder, then you probably don't have a polarity problem. If they are playing about the same level or less than the individual speakers that you measured, then you probably have one of your speakers polarity flipped incorrectly. So just once again, a polarity problem is a wiring issue, not a problem with delay. And so before you do your time and phase alignment, it's really important that you get any polarity issues identified and sorted out before you move on to the next stage. So now I've got all my wiring issues sorted out. I'm not going to have any polarity problems that's going to cause me headaches down the track when it comes to time and phase alignment, but I've still got all of these speakers all playing at once in the car. My mids, and I've got a sub, and I've got my tweeters playing, and my mid bass. They're all firing off sound waves in the car, and they're crashing into each other and doing a bunch of things. So here's a diagram. I've got 3 different speakers playing, and you can see that they're creating sine waves, but sometimes they're adding up and sometimes they're cancelling. And in this second illustration, we can see that we've got our mid. If we look at these 4 speakers, we've got our tweeters, our mids, our mid bass, and our subwoofer all vibrating at different speeds or frequencies, and in some cases they'll be adding up and others they won't. And in this final illustration, when you put it all together, you can see there's waves going all over the place. How are we going to possibly time and phase align all of these things? Well, the good news is we don't really have to, because we have already done our EQ and level matching. Let me explain. Check. So if you remember way back to the beginning of the tune, we had taken a bunch of free range measures and mic around or did some sweeps, and we ended up with all the speakers playing and a big fat mess that kind of looked like this. And if we get rid of some of those speakers and just have a look at a few, we had the left mid playing all the way from 40, even 20 hertz all the way through to 10,000 hertz. If we looked at the right mid bass, for example, it was playing pretty much all the frequency range, and and if we look at the front sub, it was kind of playing all the way up to 152 and doing this. The rear sub was playing even higher. So we had all of these speakers playing quite all over the place. And if we had left them like that, yes, we would have to try to time align and phase align them all the way through the entire sound spectrum. But we didn't do that. What we did was we ended up making some house curves for our speakers to provide a framework for our tune. So we made the mids and the mid bass and the front sub and the rear sub had these target lines. And what we did was that we then shaped our speakers to match the house curves. So our tweeter and our mids and our mid bass and our front and rear subs, right? So we did all of that type of thing. And if I just get rid of the house curves now, what we did was we shaped our speakers to match the response that we wanted them to play. So if we look up here at the very high end of the spectrum, there is really only one speaker playing 7,000 hertz, right? Well, actually there's two, because if I let's say get rid of all of that again and put on the right and left tweeter, there is two speakers playing here at 7,000 hertz. If I turn the mids on, the mids are playing it, but it's what's that, 80 down to it's 30 dB below below the level that the tweeters are playing this particular frequency, right? So we don't need to level match and phase align all of the speakers at 7,000 hertz. We just need to level match and phase align the tweeters at 7,000 hertz. And as we move down the sound spectrum, we get to, let's say, 4,000 hertz. Okay, now we've got two speakers playing that frequency. Or should say four speakers. We've got two tweeters and two mids. And so we would need to make sure that all of these speakers are phase and timed aligned at 4,000. And as we move down the frequency range, once again, we get to the point where now we've got two pairs of speakers playing a particular frequency range, and we'll continue on, and the tweeter tends to fall away, and now we get to 1,000 hertz, and once again it's just the mids playing that, so we don't need to worry about the let's turn the tweeters off. The mid bass is a long way away from 1,000 hertz, right? And as we move down the spectrum, we get to a point when then, okay, there's the mid bass pair and the mid pair are now playing this frequency from 300, and we can continue down down the spectrum. Get rid of these mids as well. There we go. And keep going. So we get to 200 hertz. This is the mid bass are playing them, the front sub a little bit, and the rear sub, but it's so low down. These really don't matter. We'll get to this point here, and okay, at 100, these front sub and mid bass need to be aligned. The rear sub is still 30 odd dB down, so no big deal. We keep going down, and once again get to 50 hertz. This is a long way down. We really need to align both the sub and the front sub around about 50 hertz. Maybe out to 38 and maybe out to 66. But I guess the point that I'm trying to make is that we don't need to EQ every speaker for every frequency, and that is the reason why we did our EQ and our level matching, was to make sure that we each speaker was playing its particular role in reproducing the sound spectrum, and not all of the speakers. So what this means is when we come to do our time alignment and phase alignment, then it's not the whole sound spectrum that is important. What is important is this crossover region here, and it's basically 10 dB either side of the crossover region, where we have two pairs of speakers playing, where we want to concentrate the most. The phase alignment outside of that area is less important. All right. So what we do is, let me give you an example. We'll take our left tweeter and our right tweeter, wherever that's gone, there it is, and we will time align those so that they're playing together. And when we measure the measure those two playing, which is number 16 and number 15, so number 15 and number 16, and we generate, we can see that the two speakers are in time because the sum of the two speakers here in orange is above, there's more volume than the individual measures, which means that these two are playing together to create a summation, right? Okay, so our first step is to time align our tweeters, right? So that's fine. We can get rid of that measure. And then when we get to, we'll then do the same for our, for our mids, time align those, and we'll sum them up. That's measurements 17 and 18, right? Let's just have a quick look. 17 and 18, and let's generate. And it's not so good because I know I haven't done the time alignment yet on these, but you can see that it's cancelling over here, and it's cancelling it's a bit choppy, which means that it's that it's out of phase here, and it's kind of half in phase there, but it's certainly in phase during this part of the response. But yeah, this needs more work, right? But the idea would be is that we would time align these two, and then when we come to time align and phase align the two pairs, and we're bringing our two tweeters in, then we're worried about getting the timing between the tweeters and the pairs correct through this crossover region. We're not worried about the tweeters and the mid alignment at this stage. We're not worried about having to align them through the entire sound spectrum. Just 10 dB either side of the crossover region, in this case would be 3.3. So 10 dB that way and 10 dB this way. But we'll talk about that a little later. So that is the reason why we did all of our EQ and level work first, and it's why you've got to make sure that you've completed that work and you're not going to make changes to it before you start your time and phase alignment. Okay, so the next topic I'd like to talk about is time alignment. Now, once again, I'm not going to get into to show you how to do the time alignment. I'm leaving that to the next tutorial when we'll go through the how you practically align your speakers and things. Today is talking about the theory, because that's what this video is all about. So let's just pull up a shot of the interior of the Audi A1, and my car, because I live in Australia, is right-hand drive. If you live in a left-hand drive country, that's fine. Just reverse all the stuff that I'm talking about. The concepts are exactly the same. But what we're trying to do is get a pair of speakers, such as a pair of tweeters or a pair of mids, or whatever it is, to play together and to be time aligned. Okay, and so we know a couple of things, that if we sit in the driver's seat, and let's just draw a line from the passenger speaker to the listening position, and a line from the driver's speaker to the listening position. The first thing we notice is that the distance from the passenger side to the listening position is longer than that from the driver's side. And that means if a sound wave is released by both speakers at the same time, it's going to take longer for the passenger sound wave to hit my ears than it is the driver's sound wave, because the speed of sound is constant, and when we the passenger speaker's sound wave has got further to travel before it gets to me. The second thing that will happen is that the passenger speaker, because it's further away, and they're both releasing the sound wave with the same amount of energy, by the time the passenger speaker gets to me, it will have less energy because it's had to travel further, it's had to push more air molecules, and therefore it will sound quieter than the driver's side speaker, right? And so generally we fix that by increasing the amplitude or the level or the volume of the passenger speaker so that they sound relatively the same when they reach our listening position. Now we've already taken care of all of that because we did our level matching when we did our EQ and level matching work, right? So we shouldn't need to play around with the levels any longer. So this is the problem when in car audio, is that we're sitting off center, and therefore we're going to have to, if we want those two sound waves coming from two separate speakers on either side of the car to sound like they're playing together, we're going to have to delay the closest speaker or add delay so that the sound wave is held by the speaker for a certain amount of time before releasing it. And when they, so the passenger side speaker will play the sound wave and it'll be traveling through the air. The driver's side speaker will be holding off, waiting for the delay to sort of run out, and once the delay has timed out, it will release the sound at the right time, and the two waves will hit us at the listening position at exactly the right time, and they will sound in time and in phase. So that's the idea of time alignment. Now, because we know the speed of sound is a constant, we can actually calculate the delay that we need by looking at measuring the distance from the speaker to the listening position. So let's have a quick look at how we do those calculations. Okay, so here we are back in the car, and let's say I'm trying to figure out how much delay I need to add to a speaker or something like that. Now I know that I'm going to measure the speaker from the grill to the listening position, and I figure out that's about 2 meters, right? 2 meters in distance. So how do I figure out what the distance or delay is that I need to use? Well, it's not too hard, so let me just get rid of that little 2 meter sign. So first of all, we know that the speed of sound is constant, and so we know that in metric that is 343 meters per second, and in imperial it is 1,125 feet per second, or 1,235 kilometers per hour, or 767 miles per hour. So to get from the speaker here to my listening position to carry 2 meters traveling at 1,200 kilometers an hour, it's not going to take very long at all. In fact, we can do the calculation now that we know what the speed of sound is. So our speaker distance of 2 meters, the speed of sound is 342 meters per second. That means it would take 0.0058 seconds, or 58 1,000ths of a second, to get from the speaker to my listening position, which is pretty fast. So let's have a look at that calculation. So it is distance divided by the speed of sound in seconds. So that's 2 meters divided by the speed of sound, which is 342. And if you do that calculation, it comes out to be 0.0058 seconds. But it's very inconvenient to talk about 0.0058 seconds and stuff like that. So we use the term milliseconds, and 0.0058 seconds is equal to 5.8 milliseconds. So the sound takes to travel that 2 meters from the speaker to the listening position 5.8 milliseconds. Okay, so A millisecond, so we use milliseconds and microseconds because it's a more convenient way to describe these fractions of a second that we have to work with in car audio. So a millisecond is 1/1000th of a second, and it's usually expressed as 0.001 of a second. So on the graphs and things, you'll see, 1 ms or 0.001 seconds. And a microsecond is 1/1000th of a millisecond, right? So it's 10 to the power 6 or -6 of a second, or 0.0000001 of a second, and it's expressed with this little strange US shape. But the key takeaway is a millisecond is 1/1000th of a second, and a microsecond is 1/1000th of a millisecond. Okay, so there are some general formulas that I promised that we wouldn't talk about formulas, but I do need to share this one with you. So you can easily convert distances to milliseconds and milliseconds to distance. And so if you're using the metric system, you want to take your distance in centimeters and divide it by 34 to give you milliseconds. Or if you want to work out the distance and you know the time, then you use milliseconds times 34 will give you the distance in centimeters. Now just remember, there's 100 centimeters in a meter. Okay. I had a guy who messaged me the other day and said, "Oh, all your formulas are wrong," and that's because he was using 1,000 centimeters to a meter, not 100. So just be careful. If you're using the imperial system, then the formulas are inches to milliseconds, where you use distance in inches divided by 13.4 to give you time in milliseconds. And if you want to go the other way around, it's milliseconds times 13.4 to give you the distance in inches. So, a good way of just remembering these things, or a rule of thumb, is sound travels 34 centimeters for every millisecond. Or, so roughly in the metric system, for every meter you're away from your speaker, it's about 3 milliseconds in time. And if you're in the imperial system, then, it's about 13.5 inches for every millisecond, right? So, or the sound wave, if you want to think about it another way, the sound wave moves 34 centimeters every millisecond, or 13.5 inches every millisecond. So just knowing those numbers will allow you to easily calculate your distances, or if you know your time, if you know your distances, you can work out your delays. And if you've got your times from, for example, measuring your speakers in delay, then you can work out exactly how far they are from the listening position, or at least use these numbers to check some of your measurements make kind of logical sense. Okay, now that we've got some formulas and things to be able to work out our delays, how do you actually check that your speakers are in time with each other once you've plugged all your delays into the DSP? And so there are two basic methods for checking your time alignment. The first one is called summation, so that's checking your speakers to see that your speaker pairs are summing up and not cancelling out. And then the second method is to check the that your impulse responses are aligned at the peaks. That's if you have impulse and phase information from doing sweep measures. So let's go and have a quick look in REW around how you would do those two types of checks. So when you have your two tweeters time aligned, you should be able to check them by playing the two tweeters together and then seeing what their response is like. So for example, you should end up with something like this, where the two speakers are summing up and creating a measurement that is above the individual speaker levels by between 3 and 6 dB. So this one at the moment is 82 to 88, so that's a full 6 dB summation, which means it's perfectly time aligned, right? When you are then looking at two different speakers, so in this case let's have a look at the front sub and the, where are we, sorry folks, the front sub and the rear sub. Okay, so we're going to now time two speakers instead of a speaker pair. Once again, once you've done your time alignment, you should find that the resulting, when you play the pair together, the measurement should sum up through this crossover region. See how it's nice and flat. And if you've got some sort of phase problem or it's not aligned properly, you'll end up with a dip or a cancellation occurring through this crossover region, which is a sure sign that things aren't properly time aligned, right? So that's the way to check your time alignment. Now, if you're using impulse responses, you can also check to see whether the impulse response are lined up. So you do that in the overlays area, and we're going to go to impulse, and here we've got selected our right tweeter and our left tweeter. And if we kind of zoom in and move around a little bit, you can see that the impulse response here pretty much on top of each other. I mean, we can zoom into a crazy level, right? They're not 100% there. We could move this another 10 microseconds or something. But that's what you're looking for these the peaks of the impulse response to be lined up. So that is a quick rundown on the science of time alignment. Okay, so the last section we're going to have a look at is in relation to phase. And we're going to start by jumping back into the sine wave tool, and we're going to have a talk about a thing called T0, or our reference point. Okay, the first concept I want to talk about is this thing that we call T0. So here is T0 on a graph, and it's just an imaginary point on a line, but it's, if we can line up our graphs to this point, it makes calculating the difference between any two impulse responses or any two sine waves much easier. And I'll show you what I mean. So at the moment we have a sine wave here, and it's not starting at T0, it's over here offset by so many degrees. And if I introduce a second wave, okay, like this, for example, to work out the difference between the two, I'd have to calculate that minus that, and it's quite difficult to read on the chart, right? It would be much easier if both of these were set to 0, like this, oops, like this, and then when we have the other graph, one is starting at 0, so all we've got to do is read off the number on the scale here, and we know how far offset the other graph is. So the concept of T0 is simply about lining up your reference curve or wave with the 0 point on the graph. So let's go have a look at how that works in practice in REW. Okay, so here we are in REW, and we're looking at the impulse response of the right tweeter, and you can see that it's currently sitting here at 3 milliseconds of delay, and the T0 line is over here. Okay, so the right tweeter is closer to the driver than the left tweeter, so when we bring up the left tweeter measurement, we expect it to take longer to get to the driver position or the microphone than the right hand tweeter. So here it is sitting at about 4.13 milliseconds, and the right tweeter is about 3 milliseconds, so it's about 1.14 milliseconds difference. That's certainly one way of working it out. But as I was illustrating in the sine wave graph, you can simply click up here on impulse response actions, put the cursor at the point where you want the 0 to be. So we're going to put that right on the line, and then say set T0 at cursor. And what it does is change the scale so that now the right tweeter impulse is set at time 0. And now it's simply a matter of clicking over here and seeing that the difference is 1.1 milliseconds. So this is what we call T0. Alright, well, using this set T0 at cursor button is one way of getting the your impulse responses aligned with T0, but it's not really the right way, because often you can do that and then of course this one won't move with it, and then the distances between the impulse peaks will be different, and you leave yourself open to making mistakes. The correct way to actually set your T0 and make sure all of your speakers are relative to each other in terms of timing is to set the timing offset when you take your impulse measurements or your sweeps. And so let me explain what I mean by that, because it all sounds a bit complicated, right? So once again, the right tweeter, and in red is the left tweeter. Let's get rid of the right tweeter. Now, what we need to do is when we're taking our sweeps or impulse responses, we need to make one speaker the reference speaker to which all other speakers will be measured. And usually you would pick the tweeter that is the furthest away from the listening position, but it doesn't really matter. You can use any tweeter. And the reason that we use a tweeter is because it is quite sharp and distinct where the impulse response is compared to, example, a mid, right? Here's an impulse measure of a mid, and you can see, there's a lot more room for error. So as a reference point, we tend to pick a tweeter to be the reference to measure all the other speakers against. So at the moment, it's sitting here at 4.1 milliseconds, and seeing it's the reference speaker, we'd rather that be set at time 0, right? So that we could then easily sort of work out the distances that the other speakers are away, and not have to sort of work out, 4.1 subtract, whatever the other numbers are, right? So the way we normally do this is we would take a measurement, or sweep measurement of the speaker, and then we would go into your SPL and phase, select the speaker measurement, in this case the left tweeter, go to actions, and then hit this button called estimate IR delay. So I'll do that now, and up pops a window that says, we estimate the delay to be 4.1 milliseconds, blah, 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 blah. Do you just want to shift it, or do you want to shift and update the timing offset? And I'm going to click this because when I go back into the into the sweep measurement tool, this usually has 0 in it, like it's got no numbers in it at all. But now you can see the timing offset has that 4.1 milliseconds of delay that we saw on the impulse graph, and we saw just in that pop-up. So what that estimate IR delay has done is essentially reset things to time 0, like using this T0 at cursor button. So now you can see the left tweeter is here at T0 instead of being over here at 4 point something. And now what we do is we go and measure all the other speakers, the mids, and so we take all of our sweep measures again with this reference timing remains in the box. So that means all the other speakers will be offset by this 4 milliseconds, but that means you can then directly read their delays from the chart. So for example, if we were looking at the right tweeter, we would go, okay, well that's compared to the left tweeter, that is 3.05 milliseconds late, so it's being delayed. So therefore, if we want to time align these two, I need to punch 3.054 into my DSP and remeasure it. And when you remeasure it, you would find that the two speakers should line up on top of each other, right? So if you haven't done your sweeps by estimating your IR delay and getting a timing offset, it doesn't matter when for all the stuff that we've been doing, crossovers and all of that type of stuff. We haven't really been concerned with time or time alignment, but now we are moving on to the time alignment stage. The relative timing between all the speakers has to be accurate. So what I always do is, if I'm using sweeps, I will do this method where I'll take the first sweep, estimate the IR delay, it will give me the timing offset. I then will leave that timing offset, measure all my other speakers, and I'll do all my sweeps on all my speakers again, and then I've got a full set of measurements, and I know that relative to the left tweeter, they are all accurately measured, and then I can read off the delays that I need against the left tweeter. But like I said, I will show you how to do that when we get to the phase alignment tutorial, which is coming up soon. Okay, the next thing I'd like to just look at while we're on the impulse response screen is the shapes of the different impulse responses. So let's start with a tweeter, and this is a typical tweeter impulse response. It's got a very sharp peak, very sharp defined peak, and it's pretty compact. So from the beginning of the wave, through to the peak, so the wave's beginning at around 2.8 milliseconds to the beginning of the peak, which is about 3 milliseconds. So it's about 0.2 of a second, right? Sorry, 0.2 of a millisecond between the beginning and the peak, and so it's very distinct. So we know this is the peak that we're looking for, because at this scale of 100 to 100, we're looking for the peak that reaches the 100 mark, either positive or negative. And the other way to look at it is to change this to dBFS, where you can see the peak here reaches this 0 point on the scale. So that tells us that's the impulse peak that we're looking for as well. And so this is why, as I said, we use tweeters as a good point to set our timing reference, because they have a very distinct impulse response. And so that's the right tweeter. And where is the left tweeter? Left tweeter. Here it is here. Once again, it's got an impulse response, but this time the polarity is negative because it's pointing down. All right, so that's the tweeter. So the next set of speakers, or the next smaller speakers, is the mids. So I'm going to open up the right mid bass, and you can see the difference between the two speakers in terms of how distinct they are. So as we go down the scale in terms of speakers, from tweeters to mids to mid bass to subs, the impulse response becomes less defined and stretches out. So if I turn the tweeter, the tweeter response, if I just look at the mid, once again, here's the peak. It's hitting that 100 mark. You can flip this around, and once again, you can see the tallest of the peaks is the one we're looking for here. So that's another way of looking for it. Now, from the beginning of the response, it's at 3.34 milliseconds, and the peak is at 4.3. So about 0.9 of a millisecond. So certainly broader than the tweeter, and you can see it's quite a messy looking impulse response. So, but we've still got a pretty distinct peak, and if we brought our tweeter back in, we could quite easily time align these two. Because we can see the distinct peak and measure the delay that's required to get this mid to line up with the tweeter. All right, so that is the mid. Now, what happens when we go to a mid bass? So let's bring a mid bass up, and you can see compared to the mid bass is like way over here, and the size of the curve, and I'll have to keep scrolling out and scrolling out and scrolling out until we can see the whole of the impulse response. And this is why when you start getting into mid basses and subs, it becomes very difficult to time align them using impulse responses, and you are better suited to align these bass-centric type speakers using phase instead of impulse. But we'll push on because we're looking at the shape of the curves. Whoops, once again, let's just turn the mid off and have a look at this mid bass curve. And once again, here's the peak at 100. The problem is that you can add a bunch of different mid bass measurements that we took, and quite often this peak will move around quite a lot, from 9 milliseconds to 9.2 milliseconds to 9.6 or 0.7. So getting an accurate impulse response measure is much more difficult with the mid bass. So let's zoom in a little bit more, bring the the tweeter and the mid that we were working on before, so you can see them in comparison. And now let's bring in the front sub, which is measurement 44, and once again there's in purple the front sub. We'll have to keep scrolling out to see the wave. There it is, all of it in its glory. So it's really dwarfing these two over here. Here is the peak. Once again, it's incredibly spread out, so it's not really that useful for doing impulse measurements. And then same when we bring on the rear sub, right? Bring on the rear sub, and we've even got to scroll out even further to see it. And there's the peak there. So as I said, measuring these low frequency type of drivers compared to your mids and tweets, which have got very distinct impulse responses, it's very hard to time align them. But if you are going to try to time align them, then what you're trying to look for is not necessarily the peaks, but the point at which the graphs start to, or the knee of the graph, I think they call it, is the right technical term, which we can see is kind of, if we turn off those two, for the mid bass, it's kind of there. So if you were trying to impulse align them, you would align this peak maybe with the beginning of the curve here, or for the front sub, the beginning of the curve here somewhere, or the rear sub, the beginning of the curve over here. But that is why we often suggest that do your time alignment using impulse for tweeters and mids, and then do your time alignment for mid bass, front subs and rear subs using the phase graph. But there is another way of doing this type of alignment, and that's using what we call filtered IR. So I'm just going to use this mid bass and rear sub combination just to illustrate how this filtered IR tool can help you with your alignment. So here is the mid bass, here is the rear sub. They're interacting at about 70 Hertz. So we can go over into the overlays tool and into impulse, and now we can see, and I've got them selected, so here we can see the rear sub in blue and the mid bass in green. And you could try to align these two, 11.4 versus 35. I'm not too sure. There's a lot of difference between the two, but this is something that I discovered and have been playing around with. I'm not sure how well it works, but it looks interesting, and I'd be interested to see how it works in terms of aligning some speakers. But I share this with you so you can have a bit of a play around. Maybe you could let me know whether you have any success. But this is the way it works. You click up here on the cog icon, and with the speakers that we want to manipulate selected, we click on 1/3, and we said that the crossover was around about 70, so I'm going to pick the closest one we have, which will be 63, and you will see now we have converted the mid bass and the rear sub measures into a format which looks a bit like a wavelet, right? So we have these distinct, peaks, and we have this this very distinct peak here at 63.1 on the rear sub, and then on the mid bass we have a very distinct peak at 58.2, something like that, 58.2. So if I work out the difference between those two, it's going to be it's going to be about 5 milliseconds, right? So I'm just holding Control and right mouse button, just drawing a line between the two peaks. So it's telling me 5.01. So let's go into the other screen and add 5 milliseconds to the right mid bass, right? So we go into all SPL. The right mid bass is measurement number 42. So I'm going to go Actions, Alignment Tool, select 42, measurement 42, here we are, and then I'm going to add on 5 milliseconds of delay and hit Align Copy. So now I've got a copy of the measurement with the extra 5 milliseconds. Let's go check out the overlays, and let's turn off the measurement 42, and sure enough those two peaks are now aligned, right? So the rear sub and the mid bass, and they're now completely lined up. So that is this filtered IR way of normalizing or changing or filtering the impulse responses to give you a graph that you can kind of match up. Now, how accurate this is, I don't know, because I haven't actually used it to align speakers, but it's a pretty cool little feature, and I thought that I'd share it with you so you can try it out yourself. If you have success, leave me a note down in the comments. But next time I'm off doing some time alignment work, I'm going to give this a go and see if it works. So if you remember earlier in the tutorial, we were talking about how sine waves can change in amplitude. They can also change in terms of their frequency, right, how many cycles per second, and they could change in terms of the degree of phase shift, right, compared to the original signal. And this phase shift was described in terms of degrees. So if it was sort of 1/4 of a cycle out, it was 90 degrees out of phase. Or if it was, a half a cycle out, it was described as being 180 degrees out of phase. Now this is important because when we look at the phase graph in REW, it talks about it uses the term degrees. So let's go have a look in REW and I'll explain what I mean. Alright, so for this example I'm just going to use the front and rear subs. So here is the rear sub in purple, here is the front sub in orange, and they're kind of playing from about 100, and then they start to roll off, and down. So so let's pop into the overlay section and then bring up the phase, and here we have the front sub and the rear sub selected. And so this is the phase chart. What we have here, just looking at the window, is we've got the frequency down the bottom running from 20 Hertz all the way to 20,000 Hertz, and then we have the phase wrap, for want of a better term. So here's the zero line. So this is when things are in phase with the reference wave, and then these are sort of one half of the cycle and the other half of the cycle. So we're not really looking at the phase per se of the speakers. What we're actually looking at is the frequency versus the degree of phase that the speaker is out in relation to the reference wave. So that's a complicated way of saying this is not, you're not really looking at the raw phase of a speaker. You're looking at the difference between the reference and the speaker measurement. And if you think about the scale of the sine wave that we were looking at on the on the other tool, instead of being sort of flat, this is now flipped on its side. So you've got the 0 point, and the sine wave would go like this to 180, and then from 180 it would go like this, back to 0, right? And so, as we saw before, if we'd offset the phase of one measurement to the other, we would end up at, for example, 1/4 of a cycle out of phase, or half a cycle out of phase, or 3/4 of a cycle out of phase, right? Or a full cycle out of phase when we get to 0. And so what this line is showing us is that, if I just turn off the front sub for a minute, we just look at the rear sub numbers. The front sub at 50 Hertz, which is the crossover zone, is at 90 degrees positive out of phase with the reference curve. And what does that mean? Well, probably absolutely nothing, because this is kind of like a relative term. What's important is when we're comparing two speakers, so if I bring the front sub back in, what is the front sub doing at the same frequency, right? So the rear sub is 90 degrees out of phase, but the front sub is 47 degrees out of phase. So the difference between these guys is 43, right? 43 degrees. And that's what's important, not necessarily these numbers over here. We're measuring both speakers against a reference curve. What we're interested in is just how many degrees out of phase are they relative to each other, right? So in this case, they're about 40 out. If we get down here at, the rear sub is at minus 30 degrees out, and down here it's closer to 90 at the same frequency. We're getting close to 60 degrees of phase separation, right? And when we get to stuff like this, it's even crazier. Now, when we're looking at the phase chart, we said that these speakers are rolling off around about 100, which means that we're not really interested in all this garbage over here. We, only really interested in this part from, 120 and down. So let's highlight that by clicking on Control and right-clicking on the mouse and dragging. And then we can click in the middle of that, and there's the area of interaction between the two speakers that we're interested in. So what we're interested in is not necessarily the absolute number on the phase graph, it's the degrees of phase relative to these two speakers that we're interested in, right? So minus 77 versus minus 107, so that's 30 degrees out of phase. And what we want is these two lines to be at a minimum within 60 degrees of phase of each other, and I will explain in a moment why that's important. So I'm not going to take you through how to get these lines all lined up. That's part of our phase alignment tutorial, which is coming up shortly. But I just want to take you through and explain what you're actually looking at in the phase graph. Okay, so the next thing I want to have a look at is a tool called the phase wheel, and it gives you a bit of an idea of the amount of a summation or cancellation that you'll get depending on how in phase or out of phase two speakers are. So let me just bring up the screen. So this is the phase wheel, and it's very handy in understanding just how much summation or cancellation you'll get depending on how in phase two speakers are. You heard me say before when we were looking at the phase graph that you're trying to get your phase lines within 60 decibels of each other so that they will sum up. And I hope that using this little diagram will help. So when we look at these diagrams, we have the degree of phase going from 0 to 180 and then all the way to 360, right? So if something is 90 degrees out of phase, then we're going to read the chart here. If it's 180 degrees out of phase, then it's the chart's over here, and so on and so forth, right? And then the different colours indicate whether we get summation or cancellation, right? So the hot, warm colours are more cancellation, and the cooler colours are summation. And in fact, it's kind of summarised up here on this wheel. This is kind of summarised up here. And what this basically says is you've got 2 out of 3 chances of just taking any 2 speakers and for their speaker response to sum up. There's a 2/3 chance that you will get between 0 dB and a 6 dB gain, just by pure chance, right? And a 1/3 chance that you will get between 0 and some sort of infinite cancellation, right? So the odds are good that you will, if you just randomly align 2 speakers, that 2/3 of the time they will probably sum up, or at least not give you a worse outcome than the single speaker measures. But just exactly how much and what should you be aiming for? Well, that's what this chart here is for. So if you have them perfect in line and there is no phase difference between the 2 speakers, so it could be 2 tweeters or a tweeter and a mid, or a mid and a mid bass, then you will get a full 6 dB addition. That is the maximum amount of extra gain you will get from 2 speakers playing together, because they're perfectly in line, they're working together perfectly, and you're getting the maximum benefit of 6 dB. But you can be up to 55 degrees out of phase. 2 speakers can be up to 55 degrees out of phase, and you will still get 5 dB of summation, which is pretty good. 1 dB less than being absolutely perfect. So this green zone where 2 speakers are within 55, 60 degrees of each other and 0, or 305 degrees and 0, will give you 5 degrees of summation. And that's why I say, at a minimum you want to aim for a 60 degree difference in your phase plots on the phase chart, to make sure that they're adding up as best as they can. At least 60, because then you're going to fall somewhere in this green quadrant and have a gain between 5 and 6 dB, right? Now, if you are up to 90 degrees out of phase, then you will get a 3 dB rise. So, it gets between 60 and 90, you still get a bit of a rise, but it's only 3 dB. And if you go to 120 degrees out of phase, you'll get somewhere between a 3 dB and a 0 dB rise. Okay, and that's about the limit of all this positive. It's the limit of this green 2/3 window. And then beyond that, if you're more than 120 degrees out of phase, then you will get some degree of cancellation, somewhere between 0 and 6 dB, right? And if you are beyond that, 150 to 180, well, you're going to have 6 dB and less cancellation. Technically you could be to infinity, right? But it might be a 6 dB dip, or a 8 dB dip, or a 12 dB dip. It could be almost anything, right? So what's handy about this little chart is, if you're looking at how your speakers are summing up, or you're looking at the response of 2 speakers that you've measured together, and you're comparing them to the individual measures, and you're finding that in some areas it's adding up and in some areas it's not, it's likely that when you dig under the surface and look at the phase, you will see that the parts that are cancelling out or are close to 0 are going to be between 90 and 150 degrees out of phase. And if you fix that with an all-pass filter or something else, then you can find that that little hole in your response, or the summed response of your 2 speakers, could go from from this zone and into this zone, right? So I just want to share this tool with you. You can look up phase wheel if you want to look into it a bit more. Just Google phase wheel and a bunch of stuff will come up about it. But anyway, that's just another piece of the theory when it comes to phase and summation. So guys, that is probably enough theory on phase and time alignment and sound and a whole bunch of stuff. It's been a super big tutorial, super technical. We've covered a lot from how sound works and travels through the air and human hearing and how you convert all of that real world physics into mathematics and how that mathematics is used into REW and how to, what is the phase graph really telling you and a whole bunch of other stuff. Now, while we didn't get into the nuts and bolts of time alignment and phase alignment and how to do that practically, that was a bunch of good background information that you need. So when you do come to do time alignment, you'll understand the importance of polarity. You'll understand what you're trying to target when you're trying to do your phase alignment. You'll understand why you're using tweeters when you're trying to do your impulse alignment. You'll understand why certain speakers are summing up and why they're not. And so I think, if you've been through all this stuff and you've absorbed even 20% of it, you're much better placed to understand what is actually probably the most complicated part of the car audio tune, which is the time alignment and phase. So I'm working on those tutorials right now. I hope to drop them before the end of the month. I know everyone's patiently waiting for them to arrive because I think it's an area that everybody struggles with. But believe me, it is the most important part of the tune, and it's where the magic really happens. So guys, thank you so much for watching the video today, sticking through to the end. I appreciate everybody's views. Once again, if you've got any questions, pop them down in the comments. Otherwise, I will catch you in the next episode.